So this is lecture 6 on ordered field axioms. I'm outside today, so there may be a little bit of noise from cars and other stuff. Sorry about that. I'm hoping the wind doesn't make a lot of noise in the microphone. If so, my apologies in advance. Anyway, we're in section 1.4 today, which I'm speaking, of course, of your textbook, namely Introduction to Mathematical Analysis 1, second edition, by these three folks. Grateful to them for providing this free text for us. And so let's get into it. So so in this section, what they're going to do is they're going to share with us the axiomatic structure of the real numbers. And by axiomatic, I mean to say that you're not going to actually describe how to construct the real numbers from basic first principles, but what we'll do is describe their properties, and so then it's up to somebody else to find a model which has these properties. There are two ways I know of to actually build the real numbers from scratch, at least. The one is to take the rational numbers and construct them from scratch, and then adjoin to the rational numbers the limit point of all Cauchy sequences is called the completion of the rational numbers. That's one way we can construct the real numbers. The other way to construct the real numbers is with something called Dedekind cuts. And so those are two popular methods. Rest assured that there is a way to construct the real numbers from basic principles. And when you do that, you will have a set which has the properties that we're going through right now, which we'll take as axioms. So we have this axiom right here, axiom 1a, associativity of addition, axiom 1b, commutativity of addition, that there is a unique element 0 such that x plus 0 is x again, right? And so let me just go ahead and write down some words here. This is associative. This is commutative. And this is the uniqueness of the additive identity down there, which I won't write down. So I like the numbering that they've used. They have 1, A, B, C, and so forth. And the reason they're doing that is they're grouping the axioms which have a algebraic nature to start with. All right. So here's the 1D. Here we have, for each x there exists a unique additive inverse, right? So in other words, you could say axioms 1c and 1d together you could look at as being that addition has an additive inverse for each element. I mean, you have to know what the in order to make sense of additive inverse, like minus x, we of course need to know that there's something called 0, right? So 1a, b, c, and d together actually give the real numbers the structure of what's called an abelian group. I should also mention that, in fact, these axioms 1a through 1a, b, c, d collectively are also true if you study vector spaces, right? Like, these are properties we expect for vector addition. So now what follows here, 2a, b, c, d, these are decidedly not for vectors. These are things we'd only say for scalars, like associativity of multiplication, right? This is associativity of multiplication. And then this is multiplication commutes, right? Commutativity of multiplication. And so, I was talking about a vector space a second ago. I don't know if you guys talked about vector spaces in your matrix class or not, but when you do take linear algebra, like the full course, you should talk about vector spaces. And when you do that, you'll learn that we don't multiply vectors in general. If you have a way of multiplying vectors, then your set has more structure still. It's called an algebra. So in addition, there's a unique number we call 1, such that it's not equal to 0, and anytime you multiply a real number by 1, you get back the real number again, right? And also we have, for every non-zero real, a multiplicative inverse, all right? And we'll write either 1 over x or x inverse in this context. And finally, we have this distributive property here, right? And so, together, everything I've said so far, if you have a set with all these axioms, all right, you know, axioms 1 and 2, collectively that would give you what's called a field, all right? A field is a set where you have an addition, you have a multiplication, they behave like normal. In particular, that means for the multiplication, there's a multiplicative inverse for every non-zero element. That gives you what's called a field. There are many fields besides the real numbers. For example, the rational numbers form a field. You could take the rational numbers and you could like tack on the number square root of 2. And this set would be something like things of the form a plus b root 2, where a and b are rational numbers. And in that set, you multiply and divide just like you know, because of course you can view this as a subset of the reals, right? So q, this is said to be q adjoin the square root of 2. This is also a field. And it has, you know, again, axioms 1 and you can prove axioms 1 and 2 hold. You could even prove, I think, well, this is what I'm not sure about. Is it an ordered field? I think this is also an ordered field in the sense that we have axioms 3 hold. All right, so axiom 3 says for every x and y, you either have they're equal, one is less than the other, or one is greater than the other, right? So x is less than y, or y is less than x is another way we could say it. Notice the axioms are given in terms of less than, and then they define greater than in terms of less than flipped around. So it suffices to just define either less than or greater than. Here they've taken the tact of defining less than. So either if x is less than y, y is less than z, then x is less than z. This is the transitive property of inequality, transitive. Here we have, I'm not sure what to call this. I usually just say you can add, you can add to an inequality without changing the solution set. And here we also learn that we can multiply the inequality by a positive thing and not switch it around, right? So the real numbers complete with axioms 1, 2, and 3 in there. A, B, C, D, and E for 2. Together, this makes the real numbers what's called an ordered field. All right. So, ordered field. So, ordered field again is a set where you can multiply, you can divide, and also you have a order relation. But the real numbers, there's more than just the real numbers that are an ordered field. As he points out, rational numbers are ordered field, right? And I pointed out to you that even this thing, which is bigger than the rational numbers but smaller than the real numbers, this is what's called a q adjoin root 2 is a subfield of the real numbers. That's another ordered field. However, this ordered field and the rational numbers are really fundamentally different than the real numbers because they don't have a property which is really important to analysis, namely they're not what are called complete. So the completeness of the real numbers we'll describe by the completeness axiom, but that takes a little bit more work to describe. We have to talk about boundedness above and below and so forth, and so we'll do that in the next section. All right. So I've given a part of the description of the real numbers, but not quite the whole story yet. All right. So once you have these axioms, you can prove lots of properties for the real numbers. So And I'm not going to prove all these. I'll talk about the proofs of some of them on the next page, but you can prove this cancellation property, x plus y equals to x plus z implies y equals to z. You can prove that the additive inverse of the additive inverse is the element again. You can prove you have cancellation if you have multiplication by a non-zero x. You can cancel the x. You can prove that 1 over something is the something again for something non-zero. You can prove that 0 times anything is 0. You can prove that minus an element, the additive identity, is in fact the same as the additive inverse of the 1 times the element. You can prove that it doesn't matter if you multiply minus x times minus z or minus x times z, or take the additive inverse of the product of x and z. It's all the same thing. You can prove that if x is positive, minus x is negative, and if x is negative, then minus x is positive. And you can prove that if you have multiplication by a negative number, it flips the inequality. And you can also prove that 0 is less than 1. These are all things we could prove from the axioms, meticulously, step by step. All right? And I think it's good to see a little bit of that. So let's do that. And I'm, again, so grateful for this book. It has really, methodical and quite careful arguments, and it's very useful to us. So, actually, I give some of these same arguments in my calculus notes. When I teach calculus to to an audience which includes math majors, I actually define the real numbers axiomatically like it's done here, and I prove some of these things. But not everybody does that, right? A lot of people just say, oh, the real numbers, you know what they are, and they kind of go on from there. But it's important for us to understand what real numbers come with. They come with these axioms. And so here's the cancellation property. Suppose that we have x plus y equal to x plus z. We can add minus x to both sides. That exists by axiom 2D. So you have minus x plus y equal to minus x plus z. But axiom 1a, which you might recall is associativity, says we can instead add minus x to x first. And on the right-hand side, we can add minus x to x. But then by axiom 2D, which says that x and minus x add to 0, we get 0 plus y equals to 0 plus z, which then, by definition of 0, which is axiom 1c, gives us that y equals to z, and that proves part A of proposition 1.41, namely that we can cancel off with respect to addition. So, if I'm slightly distracted, it's because my son is scootering around me in circles. Let's see here. I don't know if you can hear him or not, but all right. So next up, where were we? So that completes the proof of this right here. Completes the proof of part A, 1.41a. So this completes proof. Completes proof of proposition 1.4.1 part A, right? And so moving on here, to prove part B, he points out, I should say they point out, there's 3 authors, right? Minus x plus x equals to 0, that means that by the uniqueness of the additive inverse, it must be that minus x is equal to x. See, because when I add that to that, I get 0. That means that the negative of this is that. And, we could keep going through these proofs, and it's kind of fun to do it. But I would say that these kind of arguments we'll certainly do in your abstract algebra class, I would think. These are the formal acts. I mean, what we're really doing is it's more akin to group theory than analysis, in my view. But it is important to go through some of these details. Let me go on here. So let me skip ahead a little bit. Let's look at the proof of I. So just to remind you, I'm trying to get to it here. So, all right. part I, let me bring it back here for a second so we can look at it. Part I is this guy. So I says that when we multiply an inequality by a negative number, it flips the inequality, right? So x less than y, z less than 0, then xz is greater than yz, right? Okay, so how do we prove that? With now let's start with, suppose x is less than y and z is less than 0. Then minus z is greater than 0 is known from, this is from proposition 1.4.1h. So assuming we've already proved part h as we're trying to do part I, right? Then, so minus z, x is less than minus z, y. That's by axiom, one of the ordered field axioms, namely 3D, that we can multiply an inequality by a positive constant and preserve the inequality as you'd expect, all right? Now what? So that gives us that minus xz is less than minus yz, right? And I'm not sure quite what was done there, but I think an easy way to get where we want to go is just to add, we can add xz to this inequality, right? Because that's one of the things we can do. We can add xz by axiom what? Axiom 3c, right? So xz, well, let's see here, minus xz plus xz is less than minus yz plus xz, right? Which gives us that 0 is less than xz minus yz, right? Using commutativity of, I mean, you could leave it the same. Fine. I'm trying to be careful here. So just to be methodical here, that gives me then that 0 is less than minus yz plus xz. Using, I used what axiom? Axiom, I want to say axiom 1D. And then we can add yz by axiom 3c. And so if we add yz by axiom 3c, we get 0 plus yz is less than minus yz plus xz plus yz, parentheses needed, right? Then this gives us that yz is less than xz. Going from here to here, I've used associativity and axiom and commutativity, right? Because I had to order the, I had to switch the order of this and that to get the yz's next to each other. And then I used axiom 1D again. I used all of those to cancel out plus yz and minus yz to just leave us xz. And that's exactly what we wanted to prove, because our goal was to show that xy, our goal was to show that x less than y and z negative implies that yz is less than xz, or equivalently, like this is equivalent to xz greater than yz, right? Which is what we usually do, flipping the inequalities. All right. So sorry about that bump in the road here. You know, I think the text is very careful, but I think that's just a typo, and probably like this could be easily fixed if I had a clear mind right now. It's probably just like one letter off or something silly, but it's close to right. But, okay. So moving along here. Next up, definition, absolute value. So the absolute value is defined. Sorry for the wind if that's too windy right now. So the absolute value is defined like such, right? The absolute value of x is, you know, given by x if x is non-negative, and minus x if x is negative. That defines absolute value. And so, moving along here. Oh, they have kindly provided us a graph of absolute value. There's what it looks like. It's y equals x for, you know, it's y equals x over here, right? It's y equals minus x over there. If you want a formula that does both at once, here's a fun fact. Y is equal to the square root of x squared. There's an algebraic formula for the absolute value function, because this is, you know, by convention, the positive square root. And so this is exactly the same as, you know, x or minus x for x less than 0, for x positive, or rather x non-negative. Same animal. All right, so what are the properties of absolute value? So proposition 1.2, they're mostly focusing on the inequality aspects of absolute value. Oh, no, I'm wrong. There he is, the multiplicativity of the absolute value. I think that they're going to let you prove A, B, and C as exercises, and I think that's good. That's good for you. You'd like some easy exercises, right? After some of the problems I gave you in Mission 1, it's going to be welcome relief to do some nice easy exercises. So this is proposition 1.42. And let's just look at the proof of the last one, because we're going to use this over and over again in this course. The absolute value of x less than m if and only if minus m less than x less than m. And we could replace less than or equals to if we replace these with less than or equals to both as well. So, let's see here. Maybe I'm going to go ahead and just do the proof by myself. All right, sorry about that edit. So I just thought about it some more, and the proof that's given in the book is okay, but I think for you guys it's helpful to have a proof which is a little bit less, perhaps, sophisticated. Well, it's not the right way to say it. My proof is more clumsy and lengthy, but I hope you can't. I hope you can follow it. So I want to prove that the absolute value of x is less than m if and only if minus m less than x less than m. So this is a biconditional proof, right? If and only if. So I decided it would be most clear if I broke up the forward and the reverse implication. All right. So here's my proof. So I'm going to work on the forward implies of the if and only if to start with. And so here's the way it goes. Assume that the absolute value of x is less than m for some positive m, right? There are two cases to consider. Either x is non-negative, in which case the absolute value of x equals to x. So absolute value of x less than m implies that x is less than m. But on the other hand, m is positive, so minus m is negative. So minus m is, something got lost in translation right there. Minus m is less than 0. And that's less than or equal to x, which is less than m. So there we go, minus m less than x less than m, and that's what we set out to prove. So that completes the proof in the case that x is non-negative. But x could be negative, in which case the absolute value of x is equal to minus x. And the absolute value of x less than m implies, of course, that minus x is less than m. And great. So if we multiply that by minus 1, that gives us that minus m is less than x, right? By that flipping the inequality by a minus rule we just found. And so minus m less than x less than 0, because we're in that case, 0 is less than m. So again, we get minus m less than x less than m. All right, so that completes the forward implication of the proof. Now the reverse implication of the proof, here we go. Conversely, suppose x is between plus and minus m, like that. If x is non-negative, absolute value of x equals to x, so minus m less than absolute value of x less than m. And so just focus on that part right there. That's what we need, absolute value of x less than m. Because we're trying to prove, this time, guys, we're working on the reverse implication, namely that this data implies that data, right? So that's what I'm working on, the reverse implication. So x positive, so we have x non-negative argument I just gave you. The other possibility is that x is less than 0. X less than 0, then absolute value of x equals minus x. And so minus m less than x less than m implies that minus x is less than m, but that tells you that the absolute value of x is less than m. Because I notice I've just changed minus x to absolute value of x. So the converse direction of the proof is actually kind of like immediately clear, and that's probably the reason when you look at the book's proof, it focuses, the book's proof really just focuses on the forward direction, because maybe their thinking is that the reverse direction is just immediately obvious, and it is pretty close to immediately obvious. But we'd like to write down obvious things here in this course. At least at this point, we need to write down obvious things. All right. Next up, the famed triangle inequality, which is of course a real big deal in any analysis course. I was a major player in a lot of the logic. Triangle inequality. Here it is. So they point out that, you know, since we have that, let's see here how to say this. This is an immediate consequence of the previous thing we just proved. So if you think about any number, it has to be between plus or minus its absolute value. All right. So, and so they're pointing out that the absolute value of x is less than or equal to the absolute value of x, which is kind of silly to say, but they're thinking of this as being the m, right? That's the thought process there. So if you think of that as being the m, then you go back up to that right there. Just that gives you minus absolute value of x less than absolute value of x, right? Okay, and then once they have that, it's pretty easy to prove the triangle inequality, because you can just notice that, you know, minus x absolute value of x less than absolute value of x, same for y. And then if we add these inequalities, as we're entitled to by the axioms of the real numbers, we get that minus, and of course that is the same as minus the absolute value of x plus the absolute value of y less than x plus y. Yeah, the wasps. I have two problems out here, guys. The one is that the ducks at some point are going to come and try to make me feed them. And the other problem is we have these huge wasps out here that kind of buzz around from time to time, and I don't think they're going to sting me, but it's slightly disconcerting. Anyway, so once you have that, then again by the previous proposition, that shows you that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y, right? And there you go. So, and then there's a corollary here. Corollary 1.4.4, the absolute value of x, absolute value of the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x minus y. If you're curious, here is where's my proof? I have a proof here somewhere of the corollary. I'll show it to you. Stop. Wind. So the corollary, here's a proof of it. There may be more clever proofs, but here's the proof I thought of today. If we look at the absolute value of x, it's equal to the absolute value of x minus y plus y, adding 0. Then by the triangle inequality, right, I have that this is the absolute value of x minus y plus y. All right, using the triangle inequality on this and that. And as such, that shows you that the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x minus y, right? But on the flip side, symmetrically, we can interchange the role of x and y in that argument, and instead of adding and subtracting y, I can add and subtract x from y, and get that the absolute value of y minus x plus x is larger than the absolute value of y. And but remember that one of the things that, I don't know if it's been stated yet or not, but something we should obviously prove is that, like, the absolute value of a is equal to the absolute value of minus a, right? So, like, absolute value of y minus x is equal to the absolute value of minus x minus y, right? So, which of course is that again, right? So, of course, you know this from previous work in mathematics. This is how absolute value works, but we are trying to prove that kind of thing at the moment. So anyway, I get that the absolute value of y minus x, absolute value of y minus the absolute value of x is less than or equal to x minus y. I've got this, I've got that, right? I mean, let me put it this way. I've got this, I've got that. But if you put those together, we've got that the absolute value of x, but the absolute value of x minus the absolute value of y is plus or minus that quantity, right? And plus or minus that quantity is exactly what I have read here and here, which goes to show you that the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x minus y, which is really hard to say but easier to prove. So anyway, there's some fun fact for you. So the absolute value has a geometric interpretation when considering numbers on a line, right? So this is an important remembrance, right? If I have 2 points, if I've got point A and I've got point B on the number line, and I want to find the distance from A to B, what do? Absolute value B minus A, right? So that is one of our guiding principles in here, and in calculus too, right? So another way to think about it is that the absolute value of A denotes the distance of the number from A to 0. And it is true, like, some people use the terminology, they use the same notation for, like, bar of a vector, because they want to think about, like, in a vector space, a vertical bar x, vertical bar is like the distance of the vector from the origin. And I've even heard professors refer to vector length as absolute value. I think that's bad practice. I think we should say that absolute value is only for real numbers. I don't even use absolute value for complex numbers. To me, like, the length of a complex number is, well, the length of a complex number, or you could say this, perhaps some people would say modulus, some people might say square root of the modulus, whatever. But anyway, so what we're doing here is noticing that the distance from x to y is less than or equal to the distance from x to z plus the distance from y to z. So, yeah. So you could draw 3 points on the number line and see that makes sense, right? And you could also see that when the equality would have to happen is a that would have to happen when what? When could you get equality here? Well, you could think about that. Um, anyway, I hope that is more than enough. I'm sorry I'm kind of been slow on this lecture, and so next up I will have to be a little bit more snappy, because next section's on the completeness axiom for the real numbers, and there's well, there are deeper things in that section. So, thanks.